Let me just share my screen. So before we start discussing the last two modules, do you guys have a question so far or clarification from our last modules, from the quizzes, or any concerns? None? Okay, so I guess none. So if you don't have a question, so just give me a thumbs up so to indicate that everything is good. All right. So 1, 2, 3, 4, 5. Okay, great. So let's now start with the module 11 or the Millman's theorem. So we will still use the same circuit, okay, just like what we have from the, if I'm not mistaken, that it started from the mesh analysis, this kind of circuit. And then we've been, using this one from that topic up to this topic, okay. So we're just basically comparing which theorem is the best for this one. So this one is actually quite similar with the superposition and then the, let's say, nodal. Okay, you could say that it's a combination of those two. Okay, so in here in Millman's theorem, the circuit is redrawn as a parallel, okay, network of branches, and each branch containing a resistor or series battery resistor combination. So in Millman's theorem, we always have this combination. So we always have the series and then a voltage source, series voltage source, a resistance, okay, a resistance, and then a voltage source which is in a series connection. Okay, we're in the same with the other branch, but that branch should be parallel with that other branch. So it should also have a voltage source and then a resistance. So the same with other branch. So if we have three uh, branches, so those three must have three voltage source and then three another resistance. Okay, so Millman's theorem is applicable only to those circuits which can be redrawn accordingly. So this is a very, very limited theorem wherein if it doesn't meet the condition right away, you cannot use Millman's theorem. Okay, but if it's applicable, then you can use this one. Why not? Okay, so here again is our example circuit used for the last two analysis methods. Okay, so again we have 28 volts, the R1 which is 4 ohm, R3 which is 1 ohm, R2 which is 2 ohm, and then the second voltage source which is 7 volts. So from this original circuit, we have to transform this one or redrawn into a parallel network of branches into something like this. So again, in this branch, you must have a voltage source and then with a series of resistance, okay, a resistor. The same with the second branch, but since we don't have a, another voltage source in here, so it will stay as it is, all right? So it doesn't have a voltage source. And then for the last one, so it's also a complete branch which has a voltage source and then a resistance. So we could say that this one met the condition, okay, because they are in parallel with each other. So you can just have two voltage source or two branches to be exact, like this one and this one. Okay, but if you only have one branch, okay, and then others are just like resistors, then you cannot apply Millman's theorem. You must at least have two parallel connection of branches which met the condition, wherein we have the voltage source and then the resistance. The same with this one. Okay, and then take note with this one. So by considering the supply voltage within each branch and the resistance within each branch, Millman's theorem will tell us the voltage across all branches. So if we have this kind of arrangement, okay, or yeah, arrangement of components, we can actually determine the voltage above and then the voltage below, or the voltage across on the entire parallel branches. Okay, so please note that I've labeled, okay, or the the website itself labeled, okay, not me, labeled the battery in the rightmost branch as B3 to clearly denote it as being in the third branch. Okay, so this is our first branch actually. So the B1, It's an indicator that this is our first branch. And for the second, this is actually our B2, though we don't have B2, okay, but we just consider this one as a second branch, okay? And the last one is the third branch, okay, being the third branch. So even though there is no B2 in the circuit, okay, so consider this one as the first, second, and then third branch. All right. So are we clear so far on how to uh, make or how to run this one into a Millman's configuration or Millman's circuit? So this is already the standard. You must always have this 3 branches. That's the minimum. If you only have 2, that's a series connection only. Okay, that's not in a series. That's not in a parallel connection. So you must at least have 3 branch for you to apply Millman's theorem. So you can have 4 or 5. Okay, but this is already the minimum. So are we clear so far regarding with this circuit of a Millman's theorem?
Yes, sir.
All right. So again, I repeat, if it's 2 branch, you cannot apply Millman's theorem because that's just a series connection. The minimum is 3. So you can have 4, 5, and then 6 branches, and so on and so forth. All right. So if you already have formed your configuration into something like this, then you can now just simply apply this formula right here. Okay. So very simple, very basic. This is the only formula that you need. So with this, you will be able to solve the voltage across all branches. So of course, we have the first branch, second branch, third branch, and then there 1 over the resistance of that branch, and then 1 over of the resistance of that branch, then 1 over of the resistance of that branch. Okay, so just by uh, equating or just by substituting all the given values right here into our uh, equation of the Millman's theorem, so you can have this one. So just solve this one using your calculator and then you will get 8 volts. So whatever you will solve from here, that's the voltage across of all the branches. Okay, so meaning this one has an 8 volts voltage that is applying in the first branch, second branch, and then the third branch. Okay, so you can actually already use that one to deduct the voltage on each branch to get the potential voltage of each branch. So for you to be able to get the voltage drop, so of course you have to apply this one all throughout your circuit or across all of your parallel branches. So in here we have positive and then the negative. So in here we just simply followed, okay, the reference. So as you guys can see right here, we have positive and then negative. So basically we have that flow of current, that kind of flow of current. So we have this positive side, and then the negative one is like our reference voltage, okay, or the reference or the ground side of our voltage source. So that's the reason why we have the positive side right here of the positive 8 volts, and then we have here the negative side of your 8 volts. Okay, so having this kind of sign right here. All right, and then from here you can just simply deduct your first voltage through to our solved uh, or calculated voltage across your entire circuit. So in here we have uh, what is this one 28. Okay, 28 minus 8 volts, so you will get a potential voltage of 20 volts right here. And then since we don't have a voltage right here, so we just simply have a positive 8 volts across this branch right here. And then for this one, we have positive 1 volt. Okay, so 8 minus 7 is positive 1 volt. So the solution for this one is, where's that one? Yeah, right here. But before that, so here's the explanation when it comes to the polarity of your calculated voltage across through your circuit. So the polarity of all voltage in Millman's theorem is reference to the same point. Okay, so just check where is the negative side of your voltage sources. That is already your reference point or the bottom wire. Okay, in here. So that's the reason why we have also the negative side of your 8 volts right here. However, if let's say the answer, or if both batteries had been connected backward, like the negative side is on the upper and then the positive side is on the bottom, okay, then just invert everything. So you will have a negative 28 volts right here, negative 7 volts, and then you will have negative 8 volts right here. Okay, so that is always your basis when it comes to putting your polarity of your calculated uh, voltage across your entire circuit. Right, so that's why I highlighted this one right here, that if it's a negative, then we have negative 28, negative 7, and then negative 8 volts. Okay, so are we clear so far on what would be the polarity of your voltage source right here? I mean voltage source, the calculated voltage across your entire circuit. Okay, hello, hello, hello. So which part you guys are confused? Okay, so again, how did we get this 8 volts right here? Just apply this formula right here. Then substitute the corresponding values and then you will get 8 volts. So initially you don't know the polarity, so you have to base it from your existing voltage sources. Okay, so wherever is your reference point, that would be also your reference point for your voltage, okay, across your entire circuit. So the same with the positive side, which is this one. All right. And then here's how we solve for the voltage drop. So in here, we just simply get, okay, and then deduct all the voltage sources on the entire circuit. So as you guys can see right here, we have positive 8 volts all throughout, and then deducted everything, okay, from our voltage branches right here. So 8 minus 28 is negative 20 volts. So that's an indicator that we have a negative 20 volts right here, okay. And then for the ER2, we have 8 volts minus 0 volts. So that's an indicator that we have 8 volts on this branch right here. And then for the last one, 8 minus 7. So the remaining voltage drop is uh, 1 volt right here, or it will give us a voltage drop of 7. Okay, that's why we have positive 1 volt right here. Okay, so that's how we compute for the voltage drop. So again, it's always positive for your calculated voltage uh, across through the entire circuit, and then the deduct the voltage individuals of your branches. Okay? That's it for the voltage drops. And then for the currents, so once you have already solved the potential voltage, okay, so in here we have a potential voltage of 20 volts, okay, because we have a voltage a drop of 8 volts right here. So, and then in here we have, you don't have a voltage drop since we don't have a voltage existing right here before. So the voltage across this one now is 8 volts. So in here we have 20 volts potential voltage, and then 8 volts potential voltage, and then 1 volt potential voltage. So in here, just get those potential voltage, and then you will get the current that is flowing on each branch. Okay, just apply Ohm's law, and then you will get this one. Then after that, you can now label your circuit. So in here, basically, uh, it did follow the positive side, okay, or the first symbol, okay, wherever is a positive symbol, that's the flow of current, okay. So in here we have positive 28 going from here to there. So the same with this one, we have positive right here. So it's now coming from top to bottom. The same with this one, from top to bottom. All right, so if you're going to check this one using the other theorem, you will get the same flow of current. So we have 5 amps right here, 4 amps, and then 1 amp. So it's only logical because again, whichever is the largest voltage source, that's most likely the one that will dominate the flow of current of your entire circuit. Okay. So we have 5 amps coming through here, and then we have two leaving currents. Okay, one will go here, and then the other one will go right here. All right, so yeah, that's it actually for the Millman's theorem. And then here are now the conclusions or the reviews. So Millman's theorem is very convenient for determining voltage across a set of parallel branches where there are enough voltage sources. So if you saw that there is at least two voltage sources, you might want to consider using Millman's theorem. But if there is only one, then this one is not applicable. Okay. And there are examples present to procedure a solution by regular series parallel reduction method. So it is also easy in the sense that it doesn't require the use of simultaneous equation. So yes, this is super quick to solve, because it doesn't require, equation number one, equation number two, equation number three, and then solve for the current right here on the left side, current on the right side. Okay. So yeah, this is one of a good theorem that they have invented for us to be able to solve the voltage drops and then the currents on each branch. Okay, well that is only if it met the condition. Okay, if there is enough voltage sources. However, it is limited in that it only applied to circuits which can be redrawn to fit this form. Okay, that's the number one limitation. So it cannot be used, for example, to solve an unbalanced bridge circuit. So with this one, you might want to use delta to Y transformation, or maybe you can also use mesh. That's also possible, mesh analysis. And even in the cases where Millman's theorem can be applied. Okay. So the solution of individual resistor voltage drops can be a bit daunting to some. Okay, the Millman's theorem equation only providing a single figure for branch voltage. So as you will see, each network analysis method has its own advantages and disadvantages. Like this one, it's already limited, if it doesn't fit the circuit itself. So it's not that flexible unlike the other theorem. Okay. So you could say that this one has a lot of disadvantages if you really wanted to apply this one in solving a specific unknown. Okay. So each method is a tool, and there is no tool that is perfect for all jobs. Well, we could say that we can arrange them from top to bottom, wherein this tool right here is super flexible, wherein you can apply this one in everything. Okay. But there are some tools like, instead of having this flexible theorem, like you can solve that one in 30 minutes. But if you're going to use the other theorem, which is on the below of that theorem, you can solve that one in just 10 minutes. Okay, so that is why it's very, very important to learn all of the ways on how to solve uh, unknowns on a certain circuit. Okay, so the skilled technician, however, carries these methods in his or her mind like a mechanic carries a set of tools in his or her toolbox. So the more tools you have equipped yourself with, the better prepared you will be for any eventuality. Okay, so I hope you guys got the idea on learning different theorems, on why you guys are learning those. Why not just learn one and then apply that one on everything. Okay. And then here's the review. So Millman's theorem treats circuit as a parallel set of series component branches. Okay. Okay, bakit 8 volts minus 20 volt? 28 volts, sir. Akala ko, sir, higher to lower voltage. Okay, so in my case, that's always the case. But in here, it considered the, okay, it considered the reference point, okay, wherein if you're going to take a look on this one, we have here the reference point and then the positive point. And if you're going to take a look at this one, they have the same flow of voltage, right? I mean, they have the same symbols like positive here and then negative down below. And since we know, okay, that upon crossing a resistor, it will give us a voltage drop, not an additional voltage. Okay, so that's the reason why it became like 8 minus 28. Okay, So yeah, that one is really quite confusing at first, but once you've learned that, you have to consider the reference point only for the this one, and you will learn somehow that that's not how it works in Millman's theorem. Okay, because if you're going to consider the symbols of this one and this one also at the same time, it will give you 36 volts, right? But since we're getting the voltage drop, so we have to deduct. Okay, so 8 minus 28. And then one more thing, so the reason why it's 8 minus 28 is because that's how we solve for the voltage drops. So that's the reason why it was mentioned right here that the solution for individual or resistor voltage drop can be a bit daunting to some. Okay, because it's really quite weird to solve the voltage drop into something like that. Okay, but here's the pattern again. If you wanted to solve the voltage drop, it would be always your calculated voltage, okay, of the entire circuit minus, okay, minus all of the individual voltage on the branches. Okay, so that's always the case. So that is why it has here an indicator that 8 minus 28 volts, so we have negative on top. So this is already an indicator that this is the flow of current. So negative on top, meaning that's where the current will go. So again, it's the opposite of what I do or what I have teach to you guys. So if you're going to take a look on this one, we have the negative side right here, but we have the flow of current from positive to negative. Okay? So medyo magulo, 'di ba? Pero parang baliktad, it's like the opposite of everything that I have taught to you guys, because the process that this one have used is the other way around. Let's just say that it's the uh, I'm using the conventional method, right? Tama ba? Conventional ba ako? This one is using a electron. Kalimutan ko yung isang term. Yeah, it's electron uh, method. Tama ba yun? Electron. But yeah, it's considering the negative side, okay, of your voltage drop. So in here we have the positive going to negative, positive going to negative. So that's the reason why we have that flow of current, and then positive going to negative. But then again, if you're going to take a look on the voltages itself, it's only logical that we have that flow of current, since this one has the highest voltage source. So basically, we have this flow of current right here, and then it will flow on the second branch and then the third branch. So this flow of current, or yeah, flow of current right here will be dominated by this left side branch. Okay, so yeah, I hope you guys got the idea. Any questions so far? All right. So any other questions, since we are already done with the Millman's theorem? So again, all voltages entered and solved for for in Millman's theorem are polarity reference. So this is where you are considering the uh, symbols and then your flow of current. Okay, again, polarity reference. When you see polarity reference, we're talking about the reference of your entire circuit. So again, we have here the voltage sources wherein they have the same flow of polarity. We have the negative on the bottom and then positive on the upper side. So that's how we, uh, uh, let's say, verify or know what is also the polarity of your voltage solved across the entire circuit. Okay, so yeah, and then here's the reference. This one came from All About Circuits, and then here are the other related topics. So we have another one which is coming from All About Circuits, and then we have one reference here wherein coming from Circuit Flow. So make sure to check those other articles for more information when it comes to Millman's theorem. And then here are the sample videos that you guys could check. So this all of those videos came from YouTube. So make sure to visit this one, okay, for more example. So yeah, that's it for the Millman's theorem. Just a real quick uh, explanation. So all you need to do, all you need to memorize is this equation right here. So that's the formula on how to solve for the voltage across all branches. Then after that, you can now solve for the voltage drop, and then you can now solve for the branch currents. Okay, so any questions so far regarding with the Millman's theorem before we proceed to the next topic, which is the maximum power transform, which is actually a lot easier. That is, if you know how to solve Thevenin's and Norton's theorem. Anyway, we'll discuss that one later. So before we proceed to the next module, again, do you guys have a question? Or if none, just give me a thumbs up. All right, so 5 out of 12. All right, so if you guys don't have a question anymore, then let's now proceed to the uh, power, maximum power transformation. Mm, Transformation. Maximum power transfer theorem, cannot transformation. All right, so to make it short, from the word itself, we are actually solving, okay, for the maximum efficiency, okay, maximum efficiency of the power or of the voltage that will flow into our call this one load resistor. Okay, so again, this load resistor right here could be any appliances. All right. So of course, we wanted to maximize everything from the source itself, like from the outlet. If we are getting the voltage or a power of let's say 220 volts, okay, and then we should be also receiving a total of 220 volts, or at least, okay, approximately, okay, 220 volts. So if not, it could be 219. So we should at least maximize the voltage that's being outputted from our voltage source right here. Okay, so that's the uh, purpose of this maximum power transfer theorem. So we wanted to solve on whether we are really getting the maximum power that's being transferred from the source to our load resistor. Okay, so okay, without further delay, so this will only be applicable, okay, you will be only be able to use this one if you know how to solve Thevenin's theorem and the Norton's theorem. So it's like a double computation, okay. So solve for the Thevenin's resistance first, okay, or the Norton's resistance. Well, either of those two, they are just the same, okay. But if I were you, just stick with Thevenin's theorem, okay, because you'll be needing the solve or calculated at Thevenin's voltage. We will not be needing the current source for the Norton. So when it comes to theorem, just stick with Thevenin's, okay. Then you can just disregard the Norton. All right. So maximum power transfer theorem is not so much a means of analysis. Okay, this is just actually an aid to system design. Okay, wherein it's like to check if we are really maximizing the amount of power that will be dissipated to our load resistance. Okay, just like what I mentioned a while ago. So again, this will only be applicable if you know how to solve from the Thevenin's, uh, and then once you have the Thevenin's equivalent voltage and then resistance, then you can now apply maximum power transfer theorem. Okay. So before we proceed to the concept itself, because we don't have that much solution or example right here, so let's go to the YouTube, since I wasn't able to include a perfect example for this one. Maximum power transfer theorem. All right, so this one came from the organic chemistry literature again. So one of the uh, blogger or tutorials that I highly recommend. Okay, so in applying maximum power transfer theorem, so you must have this equivalent circuit. Okay, before you can apply this one, so you need RTH, and then the VTH, and then the RL itself. Okay, so for you to be able to get the P max, okay, so all you need to have is this formula. Okay, so I would like you guys to take note of this formula. P max, okay, this is the maximum power um, uh, transfer that you can, this is the formula to solve for the maximum power transfer, okay, which is called Pmax. So it is equal to 1/4 VTH squared divided by the RTH. So as you guys can see, we need the VTH itself. Okay, you must have calculated, or you must have solved the correct VTH and then the correct RTH before you will get the correct value of your Pmax. Okay, so yeah, this is the only formula that you'll need, and then the rest need to uh, apply, okay, or use the theorem of Thevenin's. All right, so that's basically the idea. So this is essentially what is aimed for in radio transmitter design, because where the antenna or transmission line or the impedance is matched to final power amplifier, or we call the impedance for maximum radio frequency power output. So impedance, the overall opposition to AC and DC current, is very similar to resistance and must be equal between source and load for the greatest uh, amount of power to be transferred to the load. Okay, so again, the idea is if it's coming from AC and then it's being transformed into DC. So yeah, we have AC of 220 volts, so it's positive, negative. But when it's converted to DC, so you should get the equal source. The equal voltage that is coming from your source to your load. Okay, so we have some appliances also wherein they only need, okay, a a small amount of voltage, then it will be amplified 10 times, 20 times, 15 times. But there are some that it needs 1:1. Okay, if we're getting 220 volts on the source, we should also get 220 volts onto the load itself. So a load impedance that is too high will result in low power output. So a load impedance that is too low will not only result in low power output, but possibly overheating of the amplifier due to the power dissipated in its internal, okay, or the Thevenin or Norton impedance. Okay, so again, we need to have this kind of circuit, and for you to be able to get the maximum power transfer theorem, so we have a shortcut for that one. So instead of solving this Pmax right here, for us to be able to know, are we getting the maximum power? So in here, all you need to do is, you must have an equal Thevenin's resistance that is going to the R load. So basically, those two must be equal. So whatever is your voltage right here,